Hi student, good evening. So today we are going to see the maximum power transfer theorem. Okay, so maximum power transfer in AC circuit. How the maximum power delivered. Okay, so how much maximum power is delivering through the load in AC circuit. Okay, so that we are going to see here. So let's see with an example. So that is what I have one voltage source. I have one voltage source that is with 2 cos 1000 t. 2 cos 1000 t volt of source voltage is there, and here is inductance, and here is one resistance, and this is capacitance. This is again resistance, and which one is my load? This is my load. Okay, this one is my load. So this is my RL, load resistance, and this resistance value is 4 ohm, and this capacitance value is 200 microfarad, and this inductance value is 2 millihenry. 2 millihenry. We have to find the maximum power that is delivering through this load. How much maximum power is there? So for that, first of all, we have to convert this circuit. We have to apply the Thevenin equivalent across this load by removing this load. Okay, so then after applying the Thevenin equivalent, then we will calculate the maximum value of load resistance. Then after that, we will calculate what the maximum power delivering through this load resistance. Okay, so here my load is what? Real load. Okay, so let's say we are going to apply here the Thevenin equivalent. Okay, in case of Thevenin equivalent, first of all, we have to remove the load RL. So I am going to remove this load resistance, and now we have to apply here Thevenin equivalent. First we are applying here the Thevenin equivalent voltage across this load. Okay, so now first of all, this is inductance and capacitance. First of all, we have to find the inductive reactance and capacitive reactance for this also, because it is given in farad and Henry unit. Okay, so we have to convert this unit into ohm in impedance form. That is what inductive reactance and capacitive reactance. For that, if you see, inductive reactance is what? XL is equal to what? Omega L, which is nothing but how much omega is there? 1000, and what is inductance is here, that is 2 millihenry. This milli and 1000 will get cancelled out, and we get XL is equal to 2 ohm. Okay, so similarly here capacitive reactance is nothing but that is XC is equal to what? 1 by omega C, which is equal to 1 by omega C is equal to what? This is 1000 into, and this is capacitance is 200 microfarad, which is nothing but 2 into 10 to the power minus 4. Okay, 10 to the power minus 4, it become 1 by 0.2, so which is nothing but XC is how much? 1 by 0.2 is nothing but 5 ohm. Okay, 5 ohm. If you say this, now we are going to replace this by impedance. So then what is in impedance form if we are going to write this? So this is inductance is nothing but here. Now it is, this inductance is now here. This is 2 ohm, means it is J2 ohm, because it is inductive means plus J2 ohm. Okay, plus J2 ohm, and this is capacitive reactance. Capacitive means it is minus J, how much? 5 ohm. Yes, so this is what. Now here we are going to calculate, we have calculated what? Inductive reactance and capacitive reactance in impedance form. So now see here, we are going to apply a Thevenin equivalent across this load equal. Okay, so now this is my voltage VTH, and this is what? These two elements are in series. So then I can combine this, and I can write this as 4 minus J5. Okay, 4 minus J5. So that is what I am going to write here, 4 minus J5. Now I am going to replace this by single impedance, so which is nothing but here single impedance, and which is 4 minus J5 ohm. 4 minus J5 ohm. Okay, so now here I am going to apply Thevenin equivalent across this load. Okay, so now see here, VTH Thevenin equivalent, how I can calculate this Thevenin equivalent voltage? By applying the voltage division rule across this impedance. Okay, so which is nothing but 4 minus J5 into what? This is what? 2. Okay, so if you see in polar form, this is 2 angle 0 degree volt. Okay, so which is nothing but 2 divided by here, this is total impedance. Okay, so total impedance is how much? J2 plus 4 minus j5. Okay, so when we solve this, what we will get here? So this is nothing but, if you see, this is 2 into 4 minus j5 divided by, this is how much, 4 minus j3, yes, volt. Now I have to convert this into single, because both numerator and denominator here. I will rationalize this and I will get what VTH as. VTH is equal to, by rationalizing this, what we will get here, 4 minus j5 into here 4 plus j3 divided by a square plus b square. So because this is what, this is 4 minus j3, but after rationalizing 4 plus j3, okay, so this I can write a square plus b square. Okay, so this is a minus jb into a plus jb, so which is nothing but a square plus b square, which will come what, 4 square plus 3 square. Okay, so that further I can write this as what, this will come equal to what, so this is nothing but equal to, if you see here, 4 16, this is what, 15, this is 16, this is plus 15 is nothing but 31, then it is 20 minus 20, this is what, plus 12, this is minus 8 minus j8. Okay, so this is my minus j8, and this is multiplied with 2 also, 2 divided by 25, yes, 2 divided by 25. Now if you see here, now what we are getting here, VTH is equal to 31 minus j8 into 2 divided by 25. So let's see, this is what we get here, VTH as 2 into 31 minus j8 divided by 25. If you see, this 1 by 25 is nothing but 0.04, so which is nothing but 0.04 into 2 is what, 0.08. This is 0.08 into 31 minus j8, yes. So this is my VTH, okay. So 31.08 into 31 minus j8 volt. So this is my Thevenin voltage, okay, Thevenin voltage across this. Now we have obtained what, Thevenin voltage, which we got what here, Thevenin voltage that we got, VTH is equal to 0.08 into 31 minus j8, okay, volt. So this is my Thevenin voltage. Now we are going to calculate what, Thevenin impedance across the load. As we know very well, while calculating the Thevenin impedance across the load, voltage source will get, independent voltage source will get what, will get short circuited. Okay, so independent voltage source will get short circuited. Now I am going to calculate here RTH through this, where my voltage source will get short circuited, which is independent AC voltage source. Here I am going to calculate ZTH. Okay, so this is my here ZTH, okay, ZTH. Here I am going to calculate across this. If you see these two elements, okay, how we are looking equivalent impedance. These two impedance are what, parallel. These two impedance are parallel, but looking, this is like in series, but we are taking it as open, but it is not actually open. We are calculating through this what, impedance. Impedance means what, we are applying here one test voltage and a test current, like this I and V. We are applying this. So because when this current will go and this will divide in both sides, so that's why these two impedance are in parallel. Okay, so this means that we are applying the test voltage and test current for calculation of the Thevenin impedance, okay, across the load. So that's why these two elements are in parallel, so that I can say like this. Okay, so that is what, for understanding purpose. So this is what ZTH, okay, ZTH that we are going to calculate. These two are in parallel. So then what we will get, ZTH, J2 ohm parallel, J2 ohm is in parallel with 4 minus J5 ohm. Okay, so that is what ZTH. Okay, so now I am going to rub this, then we will calculate ZTH, and we have calculated the Thevenin voltage. Okay, so what is my Thevenin impedance? ZTH is nothing but 2J in parallel with 4 minus J5. Okay, so which is nothing but, if you see this 2J into 4 minus J5 divided by 2J plus 4 minus J5. Okay, so then what we will get here, ZTH will be equal to here 2 take outside only, so j take this inside, what we will get, plus j4, this is 5 plus j4, 5 plus j4 divided by how much, this is what, 4, 2j, this is 5, actually this is what, 5, 2 minus 5 is 3, so this is 4 minus j3. Okay, so now see here, further simplifying this, what we will get here, now rationalize, after rationalizing, what we will get, 4 plus j4, 5 plus j4 into 4 plus j3 divided by here 4 square plus 3 square is nothing but 25. Yes, because after rationalizing, this is 4 minus j3 into 4 plus j3, which is nothing but 4 square plus 3 square, which is equal to 25. So then what we will get here, ZTH as 5 into 4, 20 minus 12 is what, 20 minus 12 is 8. Now here 16, this is 15, so 16 plus 15 is 31, this is 31j. So and this is multiplied with what, multiplied with 2. Yes, 2, and this is my 25. Yes, what we get here, this is ZTH is equal to 2 by 25 is nothing but 0.08. Yes, so that I can write here 0.08. So if you see, ZTH is equal to 0.08 into 8 plus 31j. 8 plus 31j. Okay, so this is my ZTH. Okay, ZTHO. So multiplying this inside, what we will get here, 0.08 into 8 is nothing but, this is 0.64, and multiplying this with this number, what we will get, 8 plus j into 8 to 4. So this is nothing but 8 to 4. 248. Yes, 248, and this is 2.48. Yes, this is 2.48. J 2.48. This is my Thevenin impedance, that we get Thevenin impedance. Okay, 0.64 plus j 2.48. And yes, now we are with the value of Thevenin impedance. Okay, so now we are available with the value of Thevenin impedance and Thevenin voltage. So what is that? Thevenin voltage, that is nothing but 0.08 into 31 minus j8. Okay, so this is nothing but what, this I can write 2.48 minus j 0.64 ohm, and ZTH that we have obtained as 0.64 plus j 2.48. Okay, so sorry, this is my Thevenin voltage and this is my Thevenin impedance. Okay, so now we are going to replace that network that we have obtained here is what, by this Thevenin equivalent voltage. Okay, so then this Thevenin equivalent circuit. Okay, so what was the circuit? Our circuit was this one. So this is my this is my inductance, and this is my resistance here, and this is my capacitance, and this was my capacitance, and this is how much, 4 ohm, this is RL, and this is 200 microfarad, and this is 2 millihenry. Okay, so this is ground, and this was my 2 cos 1000 t volt. Yes, 2 cos 1000 t volt. Okay, so means this was 2 angle 0 degree volt with frequency of 1000 radian per second. Okay, so this we have converted to Thevenin equivalent. So this is my Thevenin equivalent. So this is my ZTH. This network is equal to Thevenin equivalent. For this Thevenin equivalent that we obtained as, and this is my load, real load. Okay, so and this is my VTH here, VTH, and this is my RL, load resistance, and my VTH was what? My VTH that we have obtained as VTH, what we have obtained the VTH as 0.64 minus J 2.48 volt, 48. Okay, so this is my VTH 0.64 minus J 2.48, and my ZTH that we have obtained as ZTH is equal to 2.48 plus J 0.64 ohm. So this is my ZTH and this is my VTH that we have obtained for this AC circuit. Okay, so now we are going to find the maximum power that is delivering to this load. So this is my load current IL. So if you see the condition for when we have real load impedance, then in that case for maximum power transfer theorem, so the load impedance will be equal to, let me first rub this, then we will find the maximum power delivering through this load. Okay, so how much maximum power is delivering through this load? So this is my VTH and this is my ZTH. Okay, so this is my ZTH. This is my ZTH and this is my load, and this is my ground here, and this is my VTH, and this is my ZTH. This is my ZTH, and this is my load current here, and this is my RL load. If you see for maximum power transfer theorem, this load must be equal to what? Because this is real. This is what there is no complex. So the load is real, means my load for maximum power transfer must be equal to modulus of ZTH. So this means that RL must be equal to modulus of 2.64 plus J 0.64. Okay, so this is what my load. If we calculate this modulus is nothing but, if you see, this is nothing but square root of this 2.64 plus 0.64 square. So what we will get here, RL load is equal to, if you see here, 2.64 square plus 0.64. This is not 2.64, sorry, this is 2.48 square plus 0.64 square. This will come 2.5612, 2.56 ohm, approximately it will come 2.56 ohm. Okay, so this is what load for maximum power transfer. For maximum power transfer through this load, the value of load will be equal to modulus of this ZTH, which is complex. Okay, so the value will come approximately equal to 2.56 ohm. So now we are going to find the load current. Okay, so here, so that we have obtained the load value here. What is this load value? So that is nothing but 2.56 ohm. And here ZTH is what? ZTH is nothing but 2.48 plus J 0.64 ohm. Okay, and here this is ZTH, this is load, and here VTH is nothing but, that is VTH is 0.64 minus J 2.48 volt. So then what is my IL? Load current is nothing but VTH divided by here ZTH plus RL. Okay, so which is nothing but here VTH is what? This is 0.64 minus J 2.48 divided by, if you see ZTH here is nothing but 2.48 plus J 0.64 plus RL is nothing but 2.56 ohm. Okay, so when we solve this, what we will get here? Load current as 0.64 minus j 2.48 divided by 2.48 plus 2.56 is what? 2.48 plus 2.56 is nothing but this is 5.04 plus here j.64. Yes, now we are going to solve this. The load current will come here. Let me rub this first. The load current that we will get here, IL is equal to square root of this, square root of 0.64 square plus here 2.48 square divided by 5.04 square plus 0.64 square, okay, and angle phi. So here, what is this? If I will solve this, I will get here 0.64 square plus 2.48 square divided by 5.04 square plus 0.64 square, this, and this will come 0.50413. So IL will come, IL equal to 0.50413 angle phi, okay, angle phi. So this is the load current value, okay. So there is no need to calculate the angle, but still we can calculate as what is angle. Angle phi is nothing but here tan inverse 2.48 divided by 0.64 minus tan inverse 0.64 divided by 5.04. So this is what actually the value of angle, okay. If you see the value of angle, that we will get 2.48 divided by 0.64, 31. 2.48 divided by 0.64, this is 3.875. So this is 75.53 degree, and this will come 0.64 divided by 5.04, 0.127. So this is 0.127, 7.237. So this is 7.237 degree, and which will be equal to what? When we subtract the 75.53 minus 7.237, it will come 68.3 degree, 68.3 degree. Yes, so this is what angle phi. So therefore we get the angle 68.3. So actual value of load current that we got, IL is equal to 0.50, okay, 0.50413 angle 68.3 degree ampere of current. So this is actually the value of load current, okay. The load resistance that we know, load current we know, and then we can easily find the maximum power delivering through the load, okay. This is 0.50413 ampere current, okay, beat angle of 68.3 degree, okay. So now for how to find the maximum power delivering through the load, for that we have seen the condition. According to that condition, we got the value of load resistance, okay, and also we have got the value of load current that we got how much? 0.5041 angle 68.3 degree ampere, okay. So this much. Now if you see here, we are going to find load current, modulus of load current. What is modulus of load current? What do you mean by this current, this angle? This I can write 0.5041 into e to the power minus j, e to the power plus j, 68.3 degree. Yes, when we calculate modulus for this, is nothing but 0.5041 3 e to the power j 68.3 degree. This is modulus. This modulus e to the power j 68.3 will get what? get eliminated from this, and we get modulus of IL means load current is equal to 0.50413 ampere. Yes, ampere of current. So this is what actually the load current that we got. Yes, modulus of load current. Now finally we will get what the value of maximum power transfer through this load. How much maximum power transfer is there? So that is what PL maximum. PL maximum power transfer to the load is nothing but modulus of IL square into RL. Yes, so which is nothing but modulus of IL square is nothing but it is 0.50413 square into what is this load is nothing but 2.56 watt power is delivering through the load. So this value we will get as PL maximum is equal to how much? If we calculate this one, we will get 0.50413 square into 2.56. So that will come 0.65061. 0.6, yes, this is 0.61 watt of power. This is the maximum power that is delivering through this load. Yes, by after converting that AC complex circuit into the Thevenin equivalent, yes, by that we got the maximum power that is delivering through this load is 0.65061 watt of power. Okay, so that is what we can say that here, like this is my graph of power. What's in load? This is PL load power, and this is my load resistance RL. Yes, here is my maximum power. This maximum power is delivering through like this graph of maximum power. So this is what my maximum power at what resistance? 2.56 ohm of load resistance. 2.56 ohm of load resistance that I am getting here. Maximum power. This maximum power, how much is this? This is my maximum power PL, which is nothing but 0.65061 of watt of power that we are getting at this point. Okay, so this is how we can calculate the maximum power delivering through the real load in an AC circuit. Okay, so this is all about this. We have seen here maximum power while calculating the derivations for maximum power. When we derive the expression for maximum power condition, we have to make the differentiation of what power with respect to load is equal to 0, because this means what? This means what? Slope. Here is a slope, then dp by drl is not equal to 0. Here also dp by drl is not equal to 0. But here if you see dpl by drl is equal to what? 0, which is giving us what? RL is equal to modulus of ZTH. Yes, this is condition. Under this condition, this slope becomes 0. So at this slope becomes 0 means we get the maximum power at this condition. Okay, so by which we got the value of load resistance as 2.56 ohm. Yes, this is only the main reason why we differentiate, because at maximum power where we get the maximum peak power, there the slope becomes 0. So therefore we have to make this 0, by which we get the real load value, so which is nothing but equal to modulus of ZTH, while deriving the derivation for the condition of load resistance, so that the maximum power should deliver through this load. Okay, so that is what we can solve this problem of maximum power transfer in AC circuit. Thank you very much.